All right, everyone. This problem is very similar to the final problem in the carbon dioxide inquiry lab. So if you're struggling to get the math lined up correctly, this will help get you there with a similar problem. You'll have to apply these ideas to the specific problem that you see in the carbon dioxide inquiry lab. Change the numbers for molar ratios, change the numbers for molar masses, change the numbers for the ideal gas law, depending on the situation I make up today. So the numbers will change, but the setup is the same. The concept is the same. So in this problem, what do we have? So first thing to notice, we've got a decomposition reaction where sodium oxide, I'm using an ionic name because this is a metal and a nonmetal, so sodium oxide decomposes to form sodium and oxygen. So we'll need to balance this. And the problem itself says how many grams of sodium oxide, Na2O, so that's this one, would need to decompose to fill a 500 milliliter water bottle with oxygen. So they want 500 milliliters of oxygen gas coming from this decomposition of an unknown amount of sodium oxide. So if I'm to note this, I've got, this is my given, and it's actually O2. And this is my unknown. It's the target. So let's set up the problem like so. Far side, always your given. And then 1 conversion factor, 2 conversion factors, 3 conversion factors. That's too many conversion factors. Delete that. Right. Always start with your given. I know this is a little confusing. People get tripped up on this because, but wait, you're given the thing over here. Doesn't matter whether the given is the reactant or one of the products. It's still the given. It's the thing you know, and you always start your formula with the thing you know. In the practice problems, I have gone the way our brain likes to think about this, that you have a known amount of this, how much of this will be produced? That's the way I've done in the practice problems. But as we're elevating to trying to show a greater and greater mastery of this material, I'm going to mess with your brain a little bit. In good ways, I hope. Challenge equals growth. You will grow from this. So, import your given. 500 not grams. 500 milliliters O2. Now, that's the only number I'm going to put in until I have all my units figured out. I know it's really tempting to try to solve as you go and fill things in as you go, but more often than not, the problem is you end up getting the numbers right, but they're on the wrong side of the conversion factor. They end up being in a spot where you're going to multiply it instead of when you should have divided it. So one of the tricks is mess with units first. Make sure all units cancel. And remember, units canceling relies on whatever units were up there must go down there. Whatever units are here goes there. Units that are there go there. All right? So following that, I go milliliters O2. Well, what do I have that can convert volume to moles? Well, we've got molar volume. So if we do molar volume, the ideal gas law, we can figure this out. Now the one problem with the ideal gas law is it gives you liters, not milliliters. So I can actually get rid of the M, as long as you remember that milliliters, there are actually 1,000 milliliters in 1 liter. So 500 milliliters then is a half of a liter, right? If there are 1,000 milliliters in a liter, then I've got a half a liter up there. Another way of thinking about that, I like to put base 1 to milli. If I want to move from milli something, in this case liter, to base, I can go 1, 2, 3 decimal places, move the decimal 3 places to the left. So I can go 1, 2, 3, put my decimal right there. Ends up with the same answer, right? Half a liter. Zero 0.5 liters. Milliliters to liters, 0.5 liters. All right, that works now. Molar volume is liters. My given is now in liters. Cool. And molar volume, as the word implies, I can get moles from a volume. Liters is my volume. Moles of the same thing will be up top. So liters O2 gets me moles O2. Great. Copy the units down. Mole O2. If you can hear some whimpering, one of my dogs is dreaming over on the couch. So cute. All right. Now the middle one is going to be molar ratio. Molar ratios are coefficients from a balanced chem equation. Ours is currently not balanced, but we've got a chem equation. And, well, there's my oxygen. So I can create a molar ratio for either sodium or sodium oxide. And what do I want to know? I want to know sodium oxide. So now I'm going to go moles Na2O. All right, I'm almost there. If I were to fill in the numbers here, I would now know moles of sodium oxide. But what I actually want to know is grams. So I've got one last conversion to make. The last one that I can make is molar mass. Molar mass is from the periodic table. Right. Pluses and multiplies to account for the number of atoms that are actually there, but we can figure out molar mass from a periodic table. You have moles NaO up here. Follow the arrow. You must have the same units down below so that they cancel. Mole Na2O. And molar mass can go from moles to mass. And units of mass in SI are grams. Na2O. I'm going to pause still before doing any numbers whatsoever and make sure everything actually cancels. It better. So everything on the diagonal should be the same and therefore can cancel. Those are the same, they cancel. These are the same, they cancel. These are the same, they cancel. So cancel, 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 cancel. You're left with grams of sodium oxide, and you want to know grams of sodium oxide. Sweet, you're set. Can I make that? Yep, they're the same. So the only thing that didn't cancel is what you want. Now, let's be careful and calculate each of these. Molar volume, that's our first one to tackle. Molar volumes require the ideal gas laws. It says there, and the ideal gas law is PV equals nRT. I want to know how many liters, that's V for volume, are in 1 mole of oxygen. That way I can solve for only one thing inside this formula. Rearrange the formula, and you get V equals nRT over P. N equals the number of moles. In a molar volume problem, you always solve for 1 mole. That way you get a rate. How many liters per 1 mole? R, the constant we've been using for this, and it's just something you got to look up, 0.0821. Did I do that right? I usually have a little sticky note here to make sure I've got that number. And of course, I'm sure I threw away my sticky note. I think that's good. That's R. T is temperature in Kelvin. It's actually pretty hot in my house right now. My house is like 72 degrees. 72 degrees is somewhere around 22 degrees Celsius. Now the tricky part is temperature must be in Kelvin. Kelvin starts at absolute 0, which is negative 273 point something Celsius. It's really, really, really cold. So all you have to do is add 273 to your Celsius number, and you get 295 degrees Kelvin. This is the T you want to use. You got to use the Kelvin version, not the Celsius version. All right, that's gone. All right, what am I missing? I've got my N, I've got my R, I've got my T, I need my P. So what's the pressure? Well, here in Rochester, Minnesota, it's like 1,000 feet above sea level, I think. It's not that different than sea level. It's, atmospheric pressure-wise, it's like 1.01 atmospheres or something ridiculous like that. I've been keeping these simple and just simplifying, just like I did for you in the problem, and say that pressure, I don't know why I switched to blue, pressure equals 1 ATM, 1 atmosphere. I now have 4 variables to find. I can solve for V. V equals 1 mole times the rate constant 0.0821. There's a complicated unit there that I'm just skipping for simplicity. Multiplied by temperature in Kelvin, 295, divided by pressure, 1. All right, everybody's plugged in. Do the math on this real quick. 1, don't really need to do that, but times 0.0821 times 295. Don't really need to divide by 1 because the number stays the same, but hey, let's be thorough. Divided by 1 gets me 4.2195. I'm just going to round that to 2. And that is volume, and it's liters for the particular unit of volume. In your problem, you're going to get something similar. In your problem, I gave you a different temperature, probably a more normal temperature for a house, depending on where you're at. But otherwise, everything's the same. So you're really just going to mess with a different Kelvin temperature. So you're going to get a number very close to this. This is the number of liters. Oh, did not mean to do that. This is the number of liters per 1 mole. So my 1 mole is already there. Now I just need to drop that in. So 4.22 liters of oxygen per 1 mole. All right. Next step. Molar ratio with coefficients from a balanced chemical equation. Well, our problem's not balanced, so time to balance it. In doing this, remember, if the molecule's here, you have one of them. So really, there's a 1 there, there's a 1 there, there's a 1 there. And also remember, anytime that there's no subscript, like there or there, there's really a 1 there and a 1 there. And I'm going to delete those because you never actually write 1s. It is implied that if it's 0, you don't write it at all. And if it's only one of them, that you don't have to write a number. All right, but you do have to write the element. So I'm going to remove those and figure out how many sodium. 1 sodium times 2 sodium per molecule gives me 2 sodium. 1 molecule times 1 oxygen per molecule gives me 1 oxygen. 1 sodium times 1 sodium gives me 1. 1 O2 molecule times 2 O's per molecule, 1 times 2 gives me 2. Oh, what happened? All right, so we could tackle either one first. I'm going to shortcut to the one that's quicker, which is I'm going to tackle oxygen first. I can see that they are unbalanced, so I'm going to want to go to the reactant side and change the coefficient here. Remember, you are not allowed to change subscripts. I cannot just put a 2 right here. It's not allowed. That's not the molecule. You can't change the molecule, but you can change the number of molecules that are there. That's totally okay. So I'm going to put a 2 there. But calculate each thing as it happens. 2 times 2 sodium is the first thing that happens. So I end up with 4 sodium. Then you've got 2 times 1 oxygen to get my 2 oxygen. Cool. Now, tackle the sodium problem. All right, we still have a problem here. 4 to 1, but hey, this is a really easy one. I just need a 4 there so that I've got 4 times 1 to give me 4 total. Now I'm balanced. 4 and 4, 2 and 2. So to set this one up, I need to pull the coefficients. Pull coefficients from a balanced chemical equation. All right, can do. Let's look at Na2O first. Here's your coefficient for Na2O. So this is going to be a 2. And then find the coefficient for O2. Find O2 up here. Good. The coefficient that is unspoken but is there is a 1. Just to be clear, this is a 1 for a different reason than this is a 1. This is a 1 because molar volume is always per 1 mole. This is a 1 because the coefficient happens to be a 1 once it is balanced. Last step in a problem like this, where you have a given amount of a volume and an unknown amount of a mass, is to calculate the molar mass using a periodic table. For this, let's go grab, I'm going to go grab smaller little, I'm going to pull the little squares down because I can. I need sodium and oxygen. So I've got sodium. And I need oxygen. All right. The molecule itself is Na2O. All right. Well, first off, what numbers do you need from the periodic table? You do not use the whole number. That only accounts for the protons. We want to count for the average mass of all the isotopes regularly on Earth, and every sodium on average per atom is 22.990. But there are 2 sodiums. So take the mass for 1, the average mass for 1 sodium, and multiply it by 2. Great. And then add that to, well, in this case, I only have 1 oxygen, so I can just directly use that number, 15.999. Because, in this case, there is no subscript here. So, I don't need to multiply it by anything. There's only 1 oxygen. Again, you take the decimal number from the periodic table and you multiply it by the subscript. Take the decimal number from the periodic table for that element, multiply by the subscript, and if it's 1, it's no multiplication needed. Let's calculate this. 22.99 times 2. That did not work. 22.99 times 2 plus 15.999 gives me a final answer of 61.979 grams per mole. What do you mean per mole, Kyle? All right, well, this number is the mass, average mass per 1 mole of it. So when you see this per mole right here, switch to another color. What that really means is grams, that's not grass, grams per 1 mole. That's important because 1 mole needs to go right there. The number of grams part of this needs to go here. $61.979. All right, there it is. that is set up and ready to go. I've kept it in the table. Cool. You can do that. Keep it in the table if that helps. Let me quickly put it in fractions so that you can envision it that way if you like. That number times that conversion factor times this conversion factor times that conversion factor. Whatever pleases you. But at the end of the day, you are going to multiply everything on the top together. You're going to multiply everything on the bottom together. And you're going to take the product of the top divided by the product on the bottom. In other words, why those don't move. In other words, 0.5 times 1 times 2 times 61.979. Do that. Then do the bottom. 24.22 times 1 times 1. And you're all set to go. I do have another method of doing this that I have said in class. It doesn't really matter which way you do it. This is the more thorough, trackable way, so I'm going to show you that way. So let's do the top. 0.5 times 1. Don't really need to do a times 1, but times 2. Times 61.979. Yeah, that's funny. Guess what the answer is? 61.979. Because, yeah, you took that, you multiplied it by 2, and then you divided it in half. So back to the same number. Cool. Well, on the bottom, take that number times 1, you get the same answer. Times 1 doesn't do anything. Multiplied by 1, so 24.22 is the same as plugging in my calculator just to prove it to you. 24.22 times 1 times 1, 24.22. Great. Now do the division. 61.979 divided by 24.22. You can see that this is, this is going to go in. You're taking that and divided by that. You can see this number can fit in there a little more than 2 times. Cool. That makes sense with my answer. My calculator said 2.559 grams of what? Grams of Na2O. Cool. So then I would go grab my scale, pull my scale out, and mass out. You're not on camera. I don't know why I'm doing this when no one can see me. On my tablet, mass out 2.559 grams of sodium oxide. And if you could figure out how to actually make that chemical reaction work to make it decompose, I would expect if you could make it decompose and collect the gas, I'm expecting to fill a normal size, like Poland Spring size bottle of water with pure oxygen. All right, everybody. That is the little mini tutorial video for this, where we have a known amount of a product that we want, and that product is a gas. What the question is asking us to do is, how much of the reactant do you need, which is a solid, so we can measure that in grams, to get that amount of volume of a gas. In your final capstone carbon dioxide inquiry project, you will actually need to do this twice, because instead of just a simple decomposition reaction, you have a reaction that has two reactants. So you will need to do this twice for both reactants. But the cool part of doing it twice, you still start with the same amount of the gas. You still use the same molar volume for an ideal gas. And you still have the same number of moles from a balanced chemical equation. So the initial steps are exactly the same. What you need to do differently your second time around is a different number of moles, because it's a different reactant. And you need a different molar mass, grams per 1 mole. The 1 stays the same, but everything else changes because you have to look up a different compound. So the blue part would stay the same, and the orange part would be different if I had actually another reactant to account for here. All right, that is a long video, but I am hoping this gives you the confidence to complete this and feel good like you mastered the skills.